So we've had two lectures that showed a great overview of both the breadth of observations and also some of the applications available through remote sensing data. It's now time to give a bit more time to looking into that data itself, how to get hold of it, where to get it from, and how to make decisions about what data you might like. So for that, we have a fantastic invited lecturer. So I'd like to introduce Dr. Ben Loveday. So since gaining his PhD in physical oceanography from the University of Cape Town, Dr. Loveday spent most of the last decade using remote sensing techniques, numerical models, and in situ data platforms to investigate physical and biophysical processes in coastal waters and the open ocean. The work has involved multiple satellite platforms, and he's contributed to the Earth observation-based satellite services using Copernicus Sentinel-1, 2, and 3, as well as AVH-RR. His areas of scientific interest include western boundary current dynamics, interbasin exchanges, ocean response to climate modes, mesoscale variability, shelf edge exchange processes, particle tracking, looking at ecosystem connectivity, tropical storms. I mean, it's a huge list. Recently, Ben has also been working alongside EUMETSAT as a marine training service coordinator and contributed to developing tools such as the EUMETSAT Data Access Client, or UMDAC. And I think this really makes Ben an ideal person to give you all an introduction to data repositories and access for remote sensing. So with that, I'd like to hand over to Ben. Thank you.
Thank you, TJ, and thank you to my other co-hosts and for the opportunity to be here. I'm just going to share my screen, which hopefully, maybe someone give me a quick nod, you should be able to see now. So I hope you enjoyed your first two lectures in the series so far. Quite a long way to go, but after the grounding you've been given in the first two modules, I imagine that you might be thinking a bit more on the lines of, okay, this all sounds very interesting, but how do I get hold of some of this data so I can begin to work with it? And this is where I come in. So whilst TJ gave a really nice overview of some of the scientific work that I've been involved in previously, now my main job is as a trainer, and I run a training service on behalf of EUMETSAT training on Copernicus data. And a part of that is on how we actually access EUMETSAT data and the downstream products that are derived from EUMETSAT data and other data sources at the same time. Now, a little bit of a caveat before we start. If you listen to that quite long list of things I've been involved in, the main thing you should take away from that is my main thing really in my career so far is I am a data magpie, which means that I am like the little black and white bird that flies around and finds shiny things and collects it and brings it back to its nest to work with. This is my attitude and kind of my path with regards to data collection throughout the last 5-10 years of my science career. And by that, I mean that I have quite good knowledge of where the data is and how you get it, but I'm not a systems administrator or architect. So whilst I can help you with questions about where's the best place to go for something, if you ask me about the difference between a different kind of API versus another kind of API, I'm going to have a limited ability to answer that question for you. I will show you how to use those things, but I don't necessarily understand the full grain detail over how the more technical sides of that work. But that shouldn't slow us down too much in our presentation today. Okay, I'm just going to move a couple of chat boxy things out of the way. Okay, so my presentation is going to be broken kind of into two parts, and the agenda that you see here is all the first parts except for the last word you see, demos, and that's where we're going to spend half of our time. I believe in a kind of practical approach to learning, so once we've gone through a bit of an overview about where you can get some of this data, what is relevant to us, who has it, and how do we get it, we're actually going to go through some examples about using some of the platforms or portals to be able to access some of this data directly. And we'll go through some web-based services and some code-based services as well. I'll show you both. For those that are particularly interested in this, I will be one of your trainers on the at the actual symposium itself. So if you have any questions about code-related stuff, beyond the links that I share at the end of this presentation, then there'll be an opportunity to ask me there as well. So let's move on. Part one, what data are relevant to us? Our first question, usually in most cases, when we're starting with a new research topic or we're starting towards developing a new service or have a new idea, is what data do I want? And this is usually quite a complicated question. There are a series of things that we usually know when we ask this question. We think we know what variables we want, and we think we know, oh, sorry, I got a message that someone can't hear me properly, but I'm guessing everybody else can because I'm not getting any alerts. Things we usually know when we ask this are what variables we think we want and what area and time period we want to cover. But when we're working with satellite data, there's also a vast number of other questions that we should ask before we go to start to look to bring the data back to our local system or before we start probing any further. And the reason we want to ask the rest of these questions is primarily because the data is massive, really massive. We're talking about the generation of terabytes of data per day from just one agency, petabytes of data per year. At no point in our career is this data going to get smaller. So we really need to be very careful about what we look to retrieve and how we look to work with this data to make it flexible for us, especially as we start to involve ourselves in new applications that require us to use lots of data up front, such as machine learning training, making analysis ready, data for applications, etc. So that's the first reason we want to be very clear about what we want. The second reason is because the data is usually, nearly always, in different places. We are making some steps, we being the community, towards unification of this data in terms of its delivery, but it's still quite disparately kind of distributed. And the third thing is because acquisition download can be time consuming, so it's good to get it right at the first time or the first or second time to make sure we actually get what we want. Speaking from experience as someone that spent ages grabbing a load of data to find that the variable I'm interested in was not in my query, I kind of speak from experience there. So what are some of the other questions that we should ask before we even go looking for data? And I've got a long but non-exhaustive list of all the things that I could think of at the top of my head that we should probably consider when we're designing an application or when we're looking to perform some research. Most obviously, the spatial coverage of the data. Does it actually cover your area? This is maybe not as clear as it sounds. Even some low Earth orbit polar observing missions such as Sentinel-2 do not acquire data in the open ocean. So you may have an application developed where you want to look at 10 meter, 20 meter, 60 meter resolution over a given area, but actually that data just doesn't exist in the context of the open ocean. What about spatial resolution? Do you have the necessary spatial detail that you need? This is also not always a simple question. Signal to noise ratio in some satellites means that just because you have a 10 meter pixel doesn't necessarily mean you can pull out a 10 meter feature. Spectral resolution. Do you have the radiometric channels you need? What about the algorithms that are available in the products themselves? My little shorthand for this is chlorophyll 1 doesn't equal chlorophyll 2, doesn't equal chlorophyll 3. Are the standard algorithms that come with products suitable for your needs, or do you need to go looking in a slightly different way for some more fundamental data to design your own algorithms or retrievals? How often is your region sampled? Do you need to have a known time in which you have the overpass of the satellite, or is a time average suitable for you? For example, if you're looking at a more climate focused application, a time average of a day or a week or a month may be suitable. But if you're doing a matchup analysis of in situ data, then you probably want something with a known overpass time so you can connect it to your in situ record. How about the quality of the data and its availability? Do you need operational data? Do you need real-time data? Or do you need data of the highest possible quality that will really only come from a reprocessing campaign? How is this data flagged? How much data is lost in your region? Is it actually lost, or is that loss just a function of the processing it's been subjected to? How about synergy? Do you need single sensor, multi-sensor? Which works best for your application? The format, can you easily work with it? And lastly, but still importantly, the license. Can you actually get the data and work with it? With the boundaries between publicly available and commercial data becoming a little bit more blurry, it's good to check that the conditions in which you're operating the data are actually suitable for what you want to do and won't constrain you a bit further down the road. So answers to all these questions will determine really where you should go looking for your data of interest. And a lot of this depends on the level of data that you can or need to use. And what do I mean by level? So this is a partial recap of what you've seen in the first two lectures. When we talk about satellite levels, this is a highly subjective view of what we talk about when we say this is level 1 data, this is level 2, level 3, and level 4. And this doesn't apply to all instruments or all missions equally, and it doesn't apply to all sensors equally either. But this is a fairly broad brushstroke view of what we mean when we talk about different levels of data. Level 0 is essentially voltages that come off of sensors that engineers measure. It is of very limited use to us in the remote sensing community from a scientific or services perspective. And actually, it's nearly never distributed. So we can kind of ignore level 0 entirely. Level 1, both level 1A and level B, has taken those voltages and turned it into an actual measurement that a sensor has taken, usually top of atmosphere, usually at full resolution, with a known time reference, a known spatial reference, and has most of the ancillary information we need to work with the data to derive downstream or geophysical products. So this is the first level at which we kind of start to interact with the data in an expert way. Level 2 is where that top of atmosphere data has been corrected for things such as the contributions of the atmosphere to derive geophysical variables at the surface. So this is where we get our chlorophyll products, our total suspended material, our reflectances. This is where we really start to be able to work with the data in terms of the information it provides us on the ground. But it's still single sensor. So this is still the data coming from just one satellite. When we get to level 3, then we start to merge this data, usually around the similar bank of variables, with information from other satellite platforms so that we can bring them together on a uniform time space grid to complete or to add completeness and consistency between multiple different data sources, so we have fewer gaps. Now, there's a small caveat there. Sea surface topography at level 3 is still, from altimeters, is still a long track data. So we have a line of points as opposed to a swath image. At level 4 is where we start to do some more aggregation in space or time, or we start to perform some statistical technique to fill in some of the gaps in this data so that we have a more complete product. This is something that's commonly done with ocean color and sea surface temperature. And this is how we go from level 3 sea surface topography or level 3 altimetry data to a fully gridded product where we can start to derive gridded eddy kinetic energy, mean kinetic energy, etc. across the open ocean, at least anyway. Now, the reason I'm going through all of this description is that the kind of level of data you're looking at really does play a fundamental part in where you go looking for it. So I've put together a small graph here of what I think are the major kind of axes on which you can start to look at level 0 through level 4 data. So on this graph, we have an axis of convenience going from near the origin from less convenient to along the axis to more convenient. And we have an axis of flexibility. Now I'm going to explain flexibility a bit more in a second, but the flexibility goes from more flexible at the origin to less flexible as you move along the axis. So what I mean by convenience is, in general, as we move along this axis, the data becomes easier for you to use. Level 3 and level 4 data being already gridded is easier to access. It's easier for you to cut out subsets. It's easier for you to work with in long time series than the more fundamental levels of level 1 and level 2. And actually, as we move to the top right-hand side of the graph, we have this dot called images and maps. And this is just where third-party services like WebGIS providers will give you information in the form of a picture, basically, over a given region. Probably the single easiest thing for you to use. However, it's massively inflexible because you can't make any changes to it. So the flexibility axis really describes the level of decision that's already been made to bring that data to you. So flexibility, less flexibility is not necessarily a bad thing, and there's an argument that you should be working with the data at the least level of flexibility that's the best for you. Level 3 and level 4 products are less flexible only because decisions have been made beforehand about how and to what end that data is being processed. Level 1 and level 2 data are more flexible because very little has been done to them in terms of the processes that have already occurred by the time they are delivered to you. So you need to decide where on this graph you need to sit with regards to the data that you want to have access to. And there's a color coding here as well that sort of roughly describes the kind of people you would go to source this sort of data. Level 1 and Level 2 data is nearly always provided by the satellite operators and data providers themselves. So people like EUMETSAT, the European Space Agency, NASA and NOAA provide data at Level 1, A and B, and Level 2. Whereas Level 3 and Level 4 data tend to be aggregated across multiple programs and available through downstream services such as the Copernicus Marine Service or through thematic programs such as the ESA CCI program. So there is no value judgment associated with this graph. This is really a decision-making tool only about where you need to sit on this straight line in regards to how you decide what you want to get and where you want to go to get it. Okay, so that was the first part, a little bit of a quick run through on how we make selections with regards to data. The next thing I want to dwell on a little bit is who has the data that we actually want. And this could be a little bit complicated, as we will see. So under that previous graph I showed you, we had a big purple swath labeled Level 1 and Level 2. And under that category, we had a list of space agencies that may provide some of the data that you're interested in at those levels. And here is a slightly broader, but still far from exhaustive list via icons of the people that may be holding some of this data. People who we've discussed already, EUMETSAT, ESA, NASA, NOAA, also national space agencies such as CNES, particularly if you're interested in altimetry, and DLR, the German Space Agency, particularly if you're interested in SAR and altimetry also. We have the Landsat program operated by USGS. We have ocean products from Gochi through Kiost. We also have projects from JAXA, the Japanese Space Agency, ISRO, and not to forget now, because they're ever more kind of present on our scene, commercial data from the likes of Planet, who do optical satellite products, ISI, who do mostly SAR, and Digital Globe, who also do extremely high resolution taskable optical instruments. Now that column on the right hand side, I would say 5 years ago would be something that we couldn't really play with, but as more and more agreements are signed, more and more access to this data is kind of coming to the fore. I will say it is beyond ISI, which is definitively for marine purposes and iceberg tracking. The data is not quite so useful for us in the marine domain as it is for the land domain, but there are new applications and new approaches coming all the time. But mostly we're going to be dealing with the first 3 columns left to right on this graph, or rough kind of grid. Now, if only that was the whole story, but it very much is not. Beyond the actual space agencies themselves, we have a huge number of providers of data who are either strategic programs, such as the Copernicus program, downstream providers of data, such as the Copernicus Marine Service, scientific organizations, such as PML, data and cloud services, like AWS, like Wekio, like Google Earth. So there's an enormous community of people who are involved in the production and dissemination of all of the data that we want to work with, and everybody I've listed on here has some relevance to the marine domain. This is not remote sensing as a whole. This is everybody marine. That said, there is much more availability of data on the public side than there is on the commercial side for marine programs. For instance, the cloud platforms such as Wekio will give you a much better compendium of products than will AWS at the current state. But there are some very important programs for you to be aware of on here, and we're going to focus on at least one of them. But the Copernicus and the CCI programs, from an ocean color perspective, are the ones through which you will probably be looking to gather most of your data through different portals. So with that in mind, and considering that complexity, I'm just going to look at one example of how this kind of all fits together, and that example is the Copernicus program. So the Copernicus program is the European Union's Earth observation program. It's operated under the program management of the European Commission. And as you can see already from here, there are different columns below this, this top diagram associated with space, services, and in situ. And I've annotated this diagram here to show you this broad difference between the production of level 1 and level 2 data, so the fundamental satellite data, and level 3, level 4 data, which is what is available through the Copernicus services. And you can see under the space component that we have technical coordination by the European Space Agency, but the missions themselves are operated both by European Space Agency and EUMETSAT. And the data from all of those missions is fed downstream into the services, which includes the Copernicus Marine Service, Atmosphere Service, Climate Service, etc., etc. So because we have this kind of break between the level 1, level 2, and level 3, level 4, we will go to different places, usually, to get the different types of data that we want. And we can see here the various contributions of the space agencies to the services. Sentinel-3 is operated by EUMETSAT from a marine perspective, alongside Jason-3, Sentinel-6, and soon Sentinel-4 and Sentinel-5. Well, currently Sentinel-4 and Sentinel-5. Whereas information or data from Sentinel-1, Sentinel-2, and the land component of Sentinel-3 is provided by ESA, all of which are fed into the same downstream services that you see in the middle column. And there's also a component from the European Environment Agency, which contributes the in situ data, or operates the in situ part of the Copernicus program, in situ being an absolutely necessary component of any validation that we want to do from an oceanographic or ocean biogeochemistry or ocean ecosystem perspective. So this is one example of how one program brings together different providers and different services under one banner. And I think it gives you a fairly good idea of the complexity of the community out there, and so how difficult it can be for us to actually find out where our data of interest actually resides and where we might want to go to get it. So let's try and break that down a little bit more to give you an idea about the number of repositories that are operated by all these various different players that we've some of which we've highlighted already. Because again, it is not simple. We're looking at a kind of integration over 20, 30, 40 years worth of satellite data provision and upgrading of services and finding new ways to deliver data to give us a really comprehensive but quite complex landscape of the different repositories we would want to go to get the data of interest to us. For example, EUMETSAT operate, and again, this is far from an exhaustive list. EUMETSAT operate at least 4 different ways of you acquiring data through their data store, which serves Sentinel-3 operational reprocessing data, through the data center, which is an offline ordering system for most of EUMETSAT's catalog, through EUMETCAST, which is a dish receival system really for mission critical operational work with data, and EUMETView is a web visualization system, our WebGIS system. Similarly, the European Space Agency offer an open access hub for their Sentinel-1 and Sentinel-2 data. They have the CCI data portal, which links out to other services to acquire CCI data. They have the Ocean Virtual Laboratory for exploring data through a web visualizer. And they also have a new cloud data service coming soon. The mechanisms are changing quite quickly here. So there's that's the only one on here that's not a link to an actual service. When you get the presentation, the rest of these will link out to the services we're actually going to show a bit later. But the ground is constantly shifting, and I'm going to touch a little bit on how and why that's happening a little bit later on. The Copernicus Marine Service also has the Marine Data Store, and which is a series of which has a web visualizer and also a series of APIs, and I'll come to the definition of an API in a minute, as well as the My Ocean Viewer, which is a way of nicely visualizing the entire Copernicus Marine catalog on the screen. If I'm going quite quickly, do not worry, we're going to look at examples of all of these towards the demo part of my presentation later on. The WECIO Copernicus DIAS Data Information and Access Service cloud platform also has a viewer and a way of harmonizing access to all the data it holds, as well as a suite of other cloud services. NASA have their own bank of delivery systems, as do NOAA, as do ECMWF, as do EUMETSAT OCSAF, Plymouth Marine Laboratory, beyond what ESA offer for the CCI data, also operate their own ocean color portal. And I put one fairly well-known commercial operator, Synergize, in the bottom there as well, because EO Browser is something I think most people duck into and out of every now and then, because it's a nice way of displaying imagery and or acquiring data in some scales. So we have a complicated range of satellite operators, a complicated array of services, a complicated array of programs, and a complicated array of individual data access points offered by all of these. This is incredibly intimidating for a user. And I entirely appreciate this as a user myself, and still struggling to keep track of everything everywhere that everybody is operating. I nearly said everything everywhere all at once at the moment, but to be honest, it kind of is, because a lot of these operate near real-time streams, and trying to wrangle them all into one place can be a difficult thing to do. So you need to be able to decide what is your best case first guess to go and get the data that you want to start work on your application before you refine things a bit further. And that is what this fairly complicated table is supposed to show you. So what I've done is I've gone through all of those various operators, all of their various offerings in terms of the data and services they provide, and broken those down by a series of kind of themes based around individual variables that we might be particularly interested in, and then again by level. My hope here is that somewhere in one of these boxes, if you are looking for, say, ocean color level 2, because you know that you want to perform a matchup analysis, but the standard product or standard is okay for you, then one of the 4 things that I've put in that box will be suitable for your needs. And all of those, everything on this page has a provided link on the previous slide to enable you to get to it and start to work with it, or at least start to take a look around and have a tour from the word go. So because we're talking about ocean biogeochemistry and ocean ecosystems, I started with obviously ocean color at the start and listed the 4 or possibly 5 different places I think you should go to look for data from individual sensors, or from level 3, level 4 products using sensors from multiple platforms. So there's a broad break between most of them, between looking for the fundamental data, either through the EUMETSAT data store or Wekio, if you're working with Copernicus Sentinel-3 data, or looking for the NASA Earth Data Portal for NOAA Coast Watch for, I've put MODIS Plus and VIIRS Plus, because actually there's MODIS, VIIRS, CUIS, some MERIS, is all in there as well. I haven't had a chance to fully explore the entire catalog available through the NASA and NOAA portals, because me, from my own perspective, I work almost exclusively with the Copernicus data through EUMETSAT. And then at level 3 and level 4, we start to move towards the Marine Data Store, the Copernicus Marine Service, or CMEMS portfolio, either directly from their portal or via, in a cloud context, using Wekio, as well as gathering data from the ESA CCI products, including ocean color, sea surface temperature, sea level. There are an extensive number, and you'll find them all via the link that I gave above. And the similar case is really true for surface topography. We start to get slightly different when we get to radar. And by radar, I mean synthetic aperture radar, so SAR. So level 1 and level 2 data is you're best going to the Copernicus Open Access Hub that ESA operate. But that data is also made available through the Wekio cloud platform as well. And when we start to get towards some of the more synergistic or combined products at level 3 and level 4, then once again, these are made available through the CMEMS Marine Data Store. I've added another column in here for ice. There's quite significant signals occurring in both the southern and northern hemisphere with regards to ice maxima and minima respectively here at the moment. So just in case anyone was considering applications that are ice related, there is a link to the EUMETSAT OCSAF portfolio of products, which includes sea ice and winds and sea surface temperature, as well as more derived products at level 3 and level 4 through Wekio and through CCI. So this table, I'm hoping, will be a good start point for people to say, okay, I'm looking at this possible data. Can I go to some of these catalogs and start to look at what is available and how I begin to access it? As I said at the top, most of what you need, but probably nowhere near all. There are another 30, 40, maybe significantly more that I am not aware of, portals for you to access data that has more of a regional focus. I freely admit that most of my perspective here is quite global in nature, but the Copernicus Marine Service, for example, offers products that are relevant for given areas: the Iberian Peninsula, the Baltic Sea, the Arctic region, the Atlantic, and other service providers, some of which I've not listed here, also offer more spatially refined or more focused products for working in a given region. I cannot do, unfortunately, all of your detective work for you, but I can start to point you in the correct direction, I hope. So this is my advice for the best guess of who has this data, and to some extent, why they have it. Now, I've put another aside in here called user beware. So this is kind of a little bit my perspective, having shopped around for data for a good number of years. Some things to kind of be aware of, and to keep a lookout for when you are going to find the data that you're looking for. The first point is who has what is not always well advertised. This is getting better, but sometimes you will find that the thing that you want is your 20th Google search and not your first. There are often some of the best data repositories you'll find are very well hidden. It is a matter sometimes of just going digging to find out what you want, but cross-linking between services and giving credit to original data providers is getting much better. So it's a lot easier than it used to be for you to go and actually find out what you're looking for. Also be aware that collections, and my use of the word collection applies like a group of products. So all Altshi level 1B products would, for instance, be a collection, and the individual granules or swaths would be a product, are not always 100% described. So get a couple, test them first, see if they actually are what they say they are, see if they actually contain what you think they contain. And the third thing is there is replication across the community. Some products are available in multiple places. Some products are available in multiple places with different descriptions, and with the rush to deploy cloud services that host a lot of this data, cloud services are quite bad at this. By all means, before you start to acquire data, ask questions of your cloud provider. Ask them to provide specifics about the nature of the data that they have. If they can't provide you those specifics, then maybe also ask questions about whether or not they can support you later, or whether it's better you go to the fundamental data providers themselves. Formats are starting to change, and they are starting to change quickly. For now, we are lucky in the ocean remote sensing community. Nearly everything we work with is in NetCDF format, including the Sentinel Safe format. We haven't had to go through the mishmash of stuff the weather community deal with, stuff that's in GRIB, native formats, proprietary things, pretty much NetCDF across the board. Up until now, that has been pretty much fine for us. But as we move to cloud optimization and new access methods and better deployment for multiple access points, NetCDF might start to disappear in favor of things like cloud optimized GeoTIFF or ZAR, a couple of words that you might hear thrown around as different formats that data is stored in. I'm not going to go into this any further, but I'm just going to point out there that you might start to see data being offered in different formats, and the reason it's being offered in different formats is really to support large-scale workflows and cloud. And that leads me on to the third point I've got here. The storage architecture of data is starting to change. We're starting to use more object storage for what we've got, which means we're starting to kind of access data, group data in slightly different ways, and we're starting to catalog them in different ways as well, using things like Stack. And the reason we're doing this really is, again, to support cloud optimization, but really to support massive workflows, such as the production of analysis-ready data for quick decision-making, and also to support applications that require enormous amounts of data up front, such as those that need machine learning training or artificial intelligence or AI-based applications that need an enormous amount of ingestion to inform models at the start. Upscaling of processes, parallelization of processes, different access methods using things like Xarray and Dask are going to be things potentially you'll touch on in the Python components of your webinar series later on in this series. I'm not going to dwell on any of those points even further. I just want to put that in there because these might be some some terminology you'll start to encounter as you start looking for your data. Incidentally, there was a MOOC run relatively recently on AI for Earth monitoring, where you could maybe find some more information on some of these parts. Okay, that was a little bit of an aside telling you about who has what data and why they have it and how they distribute it. Now let's look at how we actually get the data that we want. And excuse me for 1 second. Okay, so how we get the data we want is, again, not quite so simple, because most of the services that I showed you before operate in slightly different ways. And so the services that they offer and the ways in which we interact with this data is kind of, to some extent, always, well, is definitely always on the move. In the past, you see, I should describe my diagram. I have 2 rows in this diagram, one called pull services and one called push services. Pull services are where we request data. We know what we want, we make an ask, and we go and get it and retrieve it locally. Push services are services that are like big pipes, like fire hoses of data that just shoot data out the end, and there's nothing we can do about the data that we get, or when we get it, it just arrives. And a good example of this is disk receival through the UMETCAR system. It delivers the data only comes really once, maybe twice if there's a backup system, and it just keeps on throwing that data down the pipe, and then you pick it up at the other end if your dish happens to be receiving it and you're collecting it in an operational way. Push services are really designed for maximum operational uptime. Pull services are designed for more flexibility to allow us to go and get what we want with more kind of fine-grained detail. And the pull service landscape of the past was a complete mishmash of different approaches, be they the original DODS service, so oceanographic data distribution systems, FTP, offline archives, loads of different HTTP or like web access protocol services such as OpenDAP, and also some WebGIS, so kind of web map or image or map delivery systems as well. These have to some extent been sort of homogenized into kind of 2 different parts, mostly by web-based APIs and OGC, Open Geospatial Consortium APIs, which tend to deal with GIS data. And even those are on the move to providing unified cloud platforms with processing APIs. And the reason for that is fundamentally, we are not going to be able to move data in the future like we are doing now. It's going to be so cumbersomely large that we're just going to have to go to the people with the data with descriptions about our processing and do it remotely and bring back the results. The data is going to be so large that almost this entire methodology of bringing data back to locally is going to have no choice but to change. This, to some extent, is my perspective, but I think you can see massive investment in the cloud market around geospatial data as a reflection of the way the wind is blowing. So we are here, and this is the part that we are going to deal with for now. We're going to touch on this. This we're going to ignore. Pretty much DODS is dead. FTP is not really around that very much. There are a few offline archives. These are still alive, the OpenDAP, HTTP, and ERDAP. I'm hoping you can see my cursor while I'm doing this, actually. Yeah, so they've all kind of been subsumed into this kind of like box that I've given here. Okay, so what does that actually mean? It means that there are kind of 2 ways that we can go about getting our data. So I've broken these 2 ways, really. These are our ways that we can get our data as kind of as people, 2 different broad approaches. There are others. I'm ignoring the others. I'm ignoring kind of I'm not going to go to that anyway. So there are 2 ways. There's a web UI way, and the web UI way is really clicking through browsers, and that's designed to support machine to human interaction. So a machine sends us up a picture, sends us up a nice menu. We do drag and drop or click boxes or draw polygons. It tells us what data matches that, and then we click another box and we download all that. Fantastic. But only fantastic if we want to get a relatively small amount of data, or that data is consistently gridded like it is in level 3 and level 4 products, and we can pull out a spatial subset and get what we want in 2 or 3 clicks. No good to us at all if we want to automate a process, or we want to know when new data arrives and we want to add that to kind of an ongoing operational system. For that, we need an API, or an application programming interface. Now, these are not designed for human readability, as you can see from the 3 examples that I put up there on the right-hand side. They are mostly a massive mess of extremely well-organized text. But what they do is allow machines to talk to machines. So this is where we start to interface with remote archives using code, using API clients, or just straight like web addresses we can type in that allow us to perform queries on a machine-to-machine way. And we're going to look at examples of both of these in the second half of my presentation. Okay, so that's the end of the first bit, and everything I do from now on is going to be a demo. So it is time to leave PowerPoint behind, and we are going to look at 5 different data providers, starting with NASA Earth data. Then we're going to look at the EUMETSAT data store, the OCCCI WebUI archive held at oceancolor.org, at Plymouth Marine Laboratory, the Siemens data portal, and then finally we're going to look at the Wekio cloud system. And I've put under here what each one of them offer, but also the bold ones are the ones I'm going to look at. So I'm not going to look at everything available from every service, or we would be here for some significant amount of time. So I am going to stop my presentation, because from now on we are going to look either at my web browser or we are going to look at the terminal. Okay. Okay, somebody want to quickly just let me know you can see my browser okay, so that I know how I'm doing. Fantastic, thank you. Okay, so first place we're going to look at is the NASA Earth Data Open Access Web UI. I'm going to use the term Web UI, Web GUI, and I'm not going to pay that much attention. I'm going to use them all interchangeably, so I ask for a little bit of your forgiveness there. But if you go to earthdata.nasa.gov, as I said, all of these links are in the presentation, which you will shortly have access to, or perhaps do already. It will bring you to this front page. Now, the nice part about this front page actually is you can click on these icons and it will take you to all the thematic parts of the various Earth data offerings. But the first place really, or one of the best places to go, you can go to get started, but actually it makes a lot of sense just to go to find data straight away. And this will, you're only now 1 or 2 clicks away from being able to actually access the data itself. The most important thing is, in order to use Earth data to its full, then you need to log into the system. So if I click on register, well, I'm actually already registered, so I don't need to register. So I'm just going to pop back, but this will give you information on how you log in. Okay, let me just pop back. So now I'm registered on the system and I'm logged in. There is a whole suite of APIs to access this data programmatically, but we're just going to go to browse by topic and we're going to find ocean. And then importantly under here, there are links to all the other DACs, and I have to remind myself what DAC actually stands for. I wrote it down somewhere. Distributed Active Archive Center. These are basically the processing centers that are responsible for the individual kind of themes for the data. For example, OB DAC is Ocean Biology DAC, and all of the MODIS ocean color products are available through here individually, as well as through this Find Data link that I'm going to click now. Okay, so this will open up the web UI for the 1,842 collections that are held on this system, which is an enormous amount. So I'm just going to give you a quick idea of how you use this system. In this top box here, you can search for collections or topics. Now you can search for generic things like sea surface temperature, but if you know a little bit more about the collection, like I said, this is an example of a collection in kind of like web catalog speak. Sentinel-1A SLC is a collection. What if I want to look for, let's go for Muir, the SST products, and I can hit enter. Let's see if that one, what that gives me. First hit it gives me is the GRIS Level 4 Muir Global Foundation Sea Surface Temperature Analysis. Okay, let's assume that I want this one. I can click on this and it will start to open up the various parts. Now, this is a global product and it's giving me 7,000 matches to that are available in this collection because I haven't done any refining by time or space at all. So this, for example, is one product available one day. So you can see it's available from April 16th to April 17th, and the nominal time is 2100. I can choose to cut that down, for example, by saying I want my start time to be, let's go today. And then for the other one, let's risk it and go today, but actually put it to yesterday. And then it will just give me the sea surface temperature map for the whole globe for the day that I have selected. And then if I want to retrieve this data, then should I have been logged in? Looks like there's something might be like a little bit funny at the moment here with my login because I changed screens. But I'll be able to click this button and download this entire global sea surface temperature product in one go. If I wanted to refine that even further or widen it, say I want 1 week's worth of SST data, I can change my start time, put it back to say the 11th. I can click download all, and I will get all of that data packaged up and downloaded as a series of .NET-CDF files. So it's a very simple way in which we can gather data. First of all, we can use it to look at the pictures. We can zoom in as we wish. It's quite high resolution and there's a lot of data behind it. So it takes a little bit of time to refine. As you can see, as I zoom in, it takes a coarse resolution and then narrows it down. But once it zooms in, then you can use this as a way of both viewing what is happening, but also download the underlying data associated with the image that you're seeing as well. So that's an example for sea surface temperature, but this is a global product. So what if we wanted to look for something a little more specific? Now I'm going to look for Modus aqua now instead. And this time I'm finding that I don't really find what I want for the first couple of hits on this list. So I'm going to use the bar on the left-hand side to focus things a little bit more specifically. So let's say, okay, I want Modus, but I want ocean chemistry. That's refined that down to 23 products. Now I'm starting to see what I want. Let's look at chlorophyll. What have we got? Okay, so now we've got some more globally binned products. But if I want to look for the level 1, level 2 data, I can refine by processing level. Oh, I've clearly done something a little bit wrong here, but I think there we go. Processing level, level 2. And we can start to look at some of the available swath data or granule data that might be in a given region. So I'm going to click on this one, and you can see that the actual options that I get in terms of the spatial refinement and temporal refinement are a bit different. Because this is swath data, we don't have global coverage. We've only got swaths that occur at a given point. And I might want to say, okay, I'm particularly interested in this point. So let's make a little rectangle. And now my search will automatically be refined by that rectangle. And I can choose to download, if I wanted to, click download all, it would download 53,723 matching granules. I don't think it's going to let me do that. It's probably going to complain, say the data is too large. But if you gave it a temporal start and end time to refine this a bit further or put a smaller box, then you start to see the sort of processes that you can engage in. So this is one example of a web GIS system, and we're going to touch on a couple that also allows access to the underlying data associated with it. There are APIs to support this, but I'm not going to go into them too much. I'm going to move on to the next service we're going to look at, which is the EUMETSAT data store. Okay, so the EUMETSAT data store can be found at data.eumetsat.int, and that will bring you to this front page. Now, whereas the NASA Earth data web UI system and APIs will give you really good access to satellites such as MODIS, VIAs, CWIFs, etc. If you want to acquire data from the Copernicus program, such as that from ALCHI or SLSTR or STRAL, or from Sentinel-6 altimetry, or from the rest of EUMETSAT's catalogue of products, then the EUMETSAT data center is the best way to come. The front end is considerably simpler, but it's got quite a powerful set of services that underlie it. So when we get to the data store, the first thing I want to do is say, right, what data have you got that satisfies my criteria? So let's go looking for ALCHI data. And it already tells me the collections that it has available on here. So Algae, it says it's found 10 results, and we have the entire available ocean catalogue of Algae data on here at level 1B and level 2. Now that means that we not only have the level 1B operational data at full resolution and reduced resolution, and the same for level 2, we also have the reprocessed data, the data that you should consider looking at if you are not limited by the need for near real-time or immediately available data, but you want the highest quality data possible to pull out a time series from. Then the reprocessed data is also available through here. And it provides a lot more information about this data itself. I'm going to look at the full resolution level 2, which is available here. If I click on learn more, then this will tell me a lot more about the collection. It will have information on product manuals, on how you use this data, on the algorithm theoretical basis documents, how these variables inside the data were actually derived. And then most importantly, probably, you can click on access data and it will open up your product selection screen. So once we get to this point, we start to see a fairly kind of similar, like a broad similarity in processes between this sort of map-based searching and these the Earth data portal. Now, there's one thing here that I want you to particularly be aware of, and that is this number. This is called the collection ID, and this is extremely important to us when we start to interface with this service via API, which we're going to do when we stop using this GUI. So again, we can go looking for, let's go for yesterday or day before yesterday today and go show results. I haven't drawn any spatial aggregation, so if we highlight a different product, then we can see this polygon moving, and we can start to see sort of like the iterational movement, if you like, of that of the satellite swath going over the surface. Now we can also spatially refine this. If we want to do an AOI, we can just, or area of interest, we can just draw a box and then we can refine our search. And we can see, okay, there were 39 products found that touch this box. So in this case, and nearly all cases, if a product touches the box, the product is included in the box. There's no limitation in this case on the percentage overlap of coverage between the two. So if I find one that I like, I can say, okay, give me some more information on this. A small quick look. This was not a good choice. This is mostly completely cloud. Not great for us. Let me, oh, it's because it's level 1B over land. Let's try and find at least one over the ocean. Let's have a little look at that guy. Ah, pretty good one. Okay, so we have some really interesting chlorophyll patterns presenting themselves in there. I say, okay, we like this one. Let's go to download it. Now it's going to complain at me when I try to download it because at the moment I am not logged into the system. Oh, let me see which one was, is that the right one? That one, there we go. If I hit download, it's going to say go to the login page and log in. So I'm going to do this. For those of you that want to use this service, you need to go to the EUMETSAT Earth Observation Portal sign in. Just Google EUMETSAT Earth Observation Portal and it will take you to the sign in form you'll need to complete to get an account. And as soon as I log in, then I'll be able to download this granule. It's great. In fact, it's going to do it automatically. It's going to remember. So I'm hoping you can see on the bottom of my screen now on my taskbar. I'm going to cancel that. It's starting to download that granule. You can also select as many as you wish. Let's say I want this one, this one, this one, this one, and add these results to my cart. Oh, I appear to have added a lot of them to my carts because my cart now has 40 different products in, and I can choose to download all of those as well. So once again, space and temporal based searching, and then download either by a direct link or into a cart that will give you a list of links that you can exploit. That's all well and good, but what if we want to do this on an automated basis? And I'm going to show you two ways of how you do this, because underlying the this web UI is a series of APIs for searching, browsing, then downloading, and also subscribing to collections. And we're going to look mostly at search and download, and I'm going to show you what those look like. So the APIs are somewhat complicated to use in nearly all cases. So to make that easier, some colleagues of mine designed a tool called EUMDAC, which stands for the EUMETSAT Data Access Client. Now, UMDAC is available on Anaconda, and again, this link is shared in my presentation, or you can also find more information on the UMETSAT webpage, and you can also find a pretty comprehensive help and usage guide on our external Confluence space. But if you come to this link, anaconda.org/UMETSAT/UMDAC, then you can find all these links to wherever you should go to get the package. So the package development is available on GitLab here with full description of what it is and what it does. But I'm just going to kind of show you how to use it for the time being. Okay, so I'm going to stop my share and we are going to now look at my terminal. Right, so this looks like a pretty boring screen. Should just be straight gray with a load of text written on it. Now, I appreciate that terminal usage is something that is not that comfortable for most people, and so I'm not going to dwell too much here. But what I will say is, for those of you who are using Linux or OS X, then you should you can use UMDAC directly from your usual terminal prompts. For those of you using Windows, because it doesn't really offer quite the same architecture, you should consider getting either the Anaconda package with the Anaconda prompt included, or something like Git Bash, which will also support terminal-based access using UMDAC. UMDAC is also available as a series of binaries if you don't want to, if you just want to install the package directly, then you can do so. Okay, so I've already installed UMDAC in my terminal. I'm just hitting enter here, it's giving me a new space. And so if I type now UMDAC in my command line, it will say, aha, I found UMDAC as a command. What do you want to do with it? And the first thing I'm going to say to UMDAC is UMDAC, but tell you what, let me just clear this screen first and make it slightly bigger. I'm going to say UMDAC describe, and I'm not going to give it any more information. And what UMDAC is going to do now is it's going to go away and give me a list of every single available collection that it knows is on the UMETSAT data store. Now it's logged in as me, so there's a whole load of stuff that's not so public, but everything that I'm going to work with now is available publicly as soon as you have a login. Actually, everything is, other than downloading, you can freely see and search for everything that's available there. So there's a lot, absolutely loads. I don't necessarily want all of that information. I want to know information on the specific collection. So let's ask it for, oh, apologies, I've got a big block in my way saying you're sharing your terminal from WebEx. So I'm going to say UMDAC describe -c, and I'm going to give it that collection name that we just had in the UMETSAT data store. So I just have to pop back to just to make sure I've got the right code. Just give me 1 second. Okay, so this is the code that I was telling you was really important for you to remember, and then I didn't remember it, but so I had to go back to the data store and look again. But I'm going to do -c for collection, and I'm going to say, UMDAC, tell me about this. Oh, and I've made a mistake here somewhere. I can't spell describe. And that's gone away and given me all the information it knows about the contents of this collection. So the description of what it is: ocean color, level 2, full color resolution from Sentinel-3. Fantastic, that's what we want. So now we've got our UMDAC collection determined. Let's decide, okay, let's go and search for the information inside this collection. So UMDAC search, and it will say, wow, there's 338,000 granules that are associated with that search. Here's a list of all of them. That is obviously far too many for what we actually want. So let us go back and say, right, let's be a bit cleverer with this. Let's go and refine our search and say, okay, we want to look for the same collection, but products between the 18th of April and the 19th of April, and a bounding box between West 10, South 10, North 10, East 10. How many satisfy that criteria? Let's just say, okay, there we go. There is the 10 or so granules that fall within that box at that time. And and all of them are available for you. Okay, so we've got a list of products that we want to search for. Now, let's say we want to download those. Now, we can actually just change search for download here, but what we can also do is dump that into a text file, which is what I'm doing now. So now if I look inside this products.txt file, I've just got a list of these granules. So I can save this for later, and I can do UMDAC download -C, my collection, and then -P, and I can use this @ symbol and say those products. Now I'm not going to hit this because I don't want to download 10 level 2 Ultra granules to my computer at the moment, but as soon as I hit go there, it will go and download those 10 products directly to my machine. So as you can see, this is this allows a lot of flexibility for you to implement code-based ways of grabbing data either on a regular time basis, or if you use the subscription API, you can trigger it to launch acquisitions as soon as a new granule is registered on the system. Or you can use it to grab lots of data that corresponds to a given search query over just a spatial area and time bounds. So you are no longer constrained to have to go through the web UI to do this. You can now just do it all programmatically. However, the command line is not for everybody. So UMDAC has another implementation that is in Python, and I'm going to show you how to do that now as well. So goodbye terminal. We're not coming back to you. We're going to go back to my web browser now. I said that, but now I've realized I might have closed my Jupyter. So let's come back to here. Ooh. Okay, so back to my web browser. All right, so that's UMDAC from the command line. What if we want to work with UMDAC from inside Jupyter Notebook? So give me 1 second. Oh, sorry, UMDAC using the Python client. So I'm just going to spin that up now, which won't take me very long. Okay, so what I'm doing is I'm spinning up something called a Jupyter Lab, which is a more modern implementation of Jupyter Notebook. If you haven't worked with Jupyter Notebook before, this is just a nice way of bringing together Python code, annotations, graphs, images to give you a more friendly, more educational, kind of more informative way of seeing how kind of code works. So hopefully you're looking at my Jupyter Notebook screen. On the left-hand side, you've just got my file manager, and in this launcher, we've just got a load of different tools that we can launch from inside Jupyter. We are on my local system at the moment. We won't be when we get towards the end of my demos, so don't worry too much about that. But I'm just going to go to a package that we've got called Learn Ulchi, and I will show you in a minute where to get this Learn Ulchi software package from, because it's all of our tutorials, all of UMetsat's tutorials based around using Ulchi data. And if I go to my index file, this will open one of my notebooks, will give you information on all of the tutorials we've got for working with this data, including one, which is advanced Ulchi data access with the UMDAC clients. And I'm going to open this one. And this will tell you some more advanced workflows that you can do with UMDAC in a Python context. So at the moment, for those that have not worked with Python and or Jupyter before, if it's in a gray box like this, it's runnable code. And if it's not in a gray box, if it's outside the gray box, then it's just decoration, either in the form of text or image or links to other resources or different parts of this individual notebook itself. So these little squares here, these little chevrons, are completely blank, which means this code has not been run. So the first thing I'm going to do is click Shift and Enter in this box and run it. And if everything goes all right, it'll give me a little number because we've actually done this already. Okay, so there we go. So all I've done there from the UMDAC Python perspective is I've got a little file here called UMDAC credentials. Now this holds critical information that you will need to use UMDAC either from the command line or through Python. And if I pop back to the UMetsat data store, and I'm just going to, oh, no, I think I've got all my own logged in. Once you do have an account, if you click on the API key button then it will give you two absolutely crucial pieces of information, your consumer key and your consumer secret. These are hidden. You can unhide them by clicking this button, which I'm not going to hide because there will be a recording of this video on YouTube. Do not share them with anyone. They are permanent, but you need those to be able to access the APIs. So remember these. And when it comes to, if you decide to work through this notebook, and it gives you instructions on how to do it in one of our introductory materials, you need to populate this file with your consumer key and your secret. This gives you this token. And once you have this token, then we can start to work with the data itself. So we're going to set the same collection ID as before. This is exactly the same process as we did in the command line, but the syntax is now in Python. We can say, right, what is this, the title of the collection I found? Ultra level 2, full resolution from Sentinel-3. Right, what is the latest product available in this collection? It's this one. You can see it's from the 19th of April at 09:45 UTC. We can say, right, let's filter by time for what products are available. Okay, let's filter by space and time for what products are available. Fantastic, we're refining the list more. Now, nicely here, you can say, what if I don't want the entire of the file? What if I only want an individual component? You can do this too, thanks to the way they're stored in NetCDF. So I've only downloaded the manifest file. I could choose to only download the chlorophyll file. I could choose to only download the tie point grid if I wanted. Any single component that is just an entire NetCDF file you can get one by one. You can also say, right, check it. Now, this is kind of a more complicated process, and I'm not going to spend too much time here for the sake of your attention span. But what I'm doing now is saying, get the latest product, get the geo coordinates, the tie coordinates, and the quality flags, then read in the quality flags, have a look at how much cloud is available in that product over my specific area of interest, and then tell me what the cover is and only download if you're more than that cover. So this is quite complicated, but this is freely shareable code. You can adapt as you see fit. But what this will do now is you can choose to implement a fairly simple workflow that will only download products over your region if it satisfies a given degree of goodness of data, depending on whatever flag recipe you pass towards that pass to that product. So if you want to say, look at, and this is not for the whole scene, this is just for your area of interest. So in this case, in my area of interest, flag pixels in black is around about 30% of my granule. The rest is deemed to be good, possibly useful data. If this was, say, 80% flagged, then maybe I will have no interest in acquiring this and I wouldn't maybe want that granule. So this is just a quick way of how you would implement UMDAC to exploit our search and download APIs to refine your data streams. Okay, so that's number 2, the UMETSAT data store through UI, UMDAC command line, and using Python. I have to remind myself what the next one we have got on our list is, but fortunately for me, I think I put them all on here in order. Before I go any further, all the code that I'm showing you here is available on the UMETSAT UMETLab GitLab instance. If you Google just the word UMETLab, then I think it brings you here. But if you go to Oceans, Ocean Training, then here you have all of the code that we provide for our various training courses, including under sensors. You will find the Learn Ultra repository, completely free for you to clone. Find this link, and full instructions are given about how to deploy and set up this this code base and go ahead and use it. If you've never used Git before, I apologize, I don't have much time to go into Git now, but it's something we'll touch on later in the actual training at the symposium itself. A note for those of you who have used Git before, you cannot just use this download. You can't just download the code, you have to clone it, and you should follow the clone instructions that are further down here, because we use this thing called submoduling, which the little downward click doesn't support. But that is all of our code for all Sentinel-3 and Sentinel-6 sensors, including how to use UMDAC to retrieve the data. Okay, so onto our next repository. Now, if you're going to be working with ocean color data on a longer time series and you want to ensure that you have the best possible synthesized multi-sensor ocean color record that is of the highest quality, then the Ocean Color CCI archive is one place you should come to get via oceancolor.org. This is operated by Plymouth Marine Laboratory, and there's 2 things I want to make you aware of. The first is there's a composite browser that allows you to look at the individual time aggregated granules or time aggregated global scenes. So let's just click on this one. And you can see then good point for a kind of one-stop coverage, if you like, of, in this case, I believe I got the monthly periods of the ocean color, and in this case, the chlorophyll fields for the entire globe. Or if I go back to home, because this is a level 3 and level 4 products, we can use an OpenDAP query to be able to pull out this data spatially. So I'm not going to go into OpenDAP too much, but if you click on OpenDAP, then you will have all of the products available for you, either aggregated as daily, 5 daily, and monthly. And clicking on all of these, you will have a raft of different ways that you can interact with this data set to be able to pull out data that's more spatially refined than just a global scene. If you do want to get the entire global record, especially at daily resolution, I think it runs to something like 80 terabytes. It might be more than that, so it'd be quite large. But you can spatially subset for a given area if you see fit. I highly recommend using this data source for anything you're looking at where a longer term time series with maximum quality in that time series is your main raison d'etre for your application. So definitely give this credence. This can also be reached via the ESA CCI main page, and that will link you out to a few other places as well. But I recommend, if you're just after just the single CCI record, just come to this record that's in here. Okay, next on my list, what have we got? Okay, and this is the second to last one, so thank you for your attention. I realize this is a very whistle-stop tour for going through all these different use cases. Next up, the Copernicus Marine Service. Now, nearly all marine products of level 3 or level 4, or sometimes level 2, that are generated by any of the satellite providers across Europe and actually even further, are included in some way in some of the downstream products in the Copernicus Marine Service. This includes level 3 and level 4 ocean color, level 3 and level 4 sea surface temperature, level 3 and level 4 altimetry, sea surface topography, ice, and you can see a full range of all of these products via the Copernicus Marine Data Store, and it's just data.marine.copernicus.eu. Again, link is provided in my presentation for when you come to it later. There is a huge array of data available on here. Because they're all level 3 and level 4 products, once again, you can spatially subset and actually pull out blocks, cubes on the fly to some extent of data that you're interested in, which means that you have to, you can be much more specific about the data that you want to gather. There is a pretty much unavoidable at this stage difference between working with level 1 and level 2, where the grid changes from product to product. Whereas level 3 and level 4, the grid stays consistent throughout every single iteration of that product. So every day, every month, every year, for example. So let's just look around inside the CMEMS portfolio for now. Let's look at, where should we go? What should we look at? Let's look at plankton. And we can see we have, okay, let's actually, I should point out here, there's a mixture in here of satellite model and in situ data. So in some cases you have reanalysis data, which is a kind of an agglomeration of them all, but you can actually break them down by just saying, I only want to see satellite observations. And you start to see some of the regionalization here. For example, you start to see different products associated with different regions, but let's go with this one. So let's look at Arctic ocean color. I don't want you want to look at Arctic, actually. I'm being a bit ambitious there. Let's try to find one that's, there we go, North Atlantic ocean color. Then we have a description of the provider of this data, what it actually contains. Actually, the CMEMS data is extremely well documented. And if you want to actually get to the data itself after reading all of this, you want to use this little downwards icon up here. So once you get to here, then you can start to do spatial and temporal subsetting of the data that you want. So in this case, let's say, again, my favorite, let's go from 0 to 45 to 10 to 40 There we go. And now we've got a nice little box that, luckily for me, because I know these coordinates spans the Northwestern Mediterranean and the Gulf of Lions. And I can say, right, I want to get this from, and this one is available only for the last week or so. Some of the collections go back 30 odd years, and more in some cases of some different variables. And it will tell me if I want to download this now. This block will to 36 megabytes, and I already know actually that it's going to be a fairly easy download for me to get. Next to this download button is a thing called API request. Now, the API on the CMEM side, we're not going to go in too much, but this will actually tell you how to acquire this data from the command line using a Python package called Motu. And if you look around inside the CMEM's website, you'll be able to see the descriptions on how you install the Python Motu client. So it can also be done from a from a program-based perspective, as opposed to going through the web UI every time. I highly recommend you explore quite thoroughly what's available on the Copernicus Marine Service website for ocean color, especially if you have a working in a European region, so that where there might be products that have more higher spatial resolution than you might get from an otherwise global product. Okay. Oh, before I move on, actually, I should also point out that if I just go back to the front page of the Copernicus Marine Service, there is another part called Ocean Visualization, which will open up a series of portals called My Ocean. I usually use My Ocean Pro. And again, this will give you your web-based display of data, kind of your WebGIS viewer of a lot of the products that you can already access through the catalog. So I have been looking recently a lot at sea ice and seawater temperature. So this will, once it's got the layers ready, tell you what, it's not got to get layers ready because I'm looking at something that's really only available polar-wise. But this will populate, and then you can also navigate through this portal as well and get information on how you download this data through API, or just acquire the image or animate the image, view the image that's on the screen. For some reason, this one isn't working too well for me right now, so I'm going to leave this one and move on to my final part. Now, my final part is called Wekio. So it is one of the Copernicus data information and access services, or DAS systems. It's a cloud-based system which almost acts like a downstream integrator of marine products at level 1 through level 4. So all of you METSAT's Copernicus, or most of you METSAT's Copernicus catalog, so everything from Sentinel-3 and Sentinel's, definitely everything from Sentinel-3, I need to check about Sentinel-6, is available through Wekio, as is most or nearly all of the products on the Copernicus Marine Service. Now, the nice thing about using the Wekio platform is it has a really, really, really large connection to the data stores that store the primary products. And that connection is not to your own local computer, it's on their own cloud platform, which means if you're moving data around, you don't have to move it to your local system. So if your bandwidth limited in any way, then Wekio provides you with a platform in which you can start to play with some of the data without having to move substantial parts of it to where you are. You only have to move back the part, post analysis, which is going to save you a significant amount of effort in terms of space. So if we go to the Wekio platform, which is at wekio.eu, and we click on data, then we will see a fairly similar web kind of display of all the data. If we click on layers, then a lot of what we see here, and you can see that it's not limited to just the Marine Service, but from a marine perspective, that's the one we're most focused on. There's data from the Climate Service, Atmosphere and Emergency Services, Land Service, Sentinel-3. I should have been a bit more confident in myself. Sentinel-6 data is also available here. You can search by area, by time. So if we want to look, say, for example, for Sentinel-3 Ulchi data, that's level 1, level 2, it should be in here somewhere. Ooh, hang on. Let's refine a bit further. Ulchi level 2 reprocessed data made available from UMETSAT but passed through to the Wekio system. And the same thing is true for the operational data, which is just the data that comes through on a minute by minute basis. We can add this to our map, and we can show the current kind of graph of, or the current representation of the chlorophyll field for today. And then we can choose if we want, as before, to set an AOI. And then when we look at, let me get rid of Sentinel-2 true color because it's quite large. Now, it won't let me download until I'm signed in, so I highly recommend that you go to the Wekio system and log in for an account. And you can see here, now I'm logged in. I got my little B up here for my first initial. I can copy my AOI from my map, and I can either request that data or I can show API request. Now, the nice thing about the Wekio system is it will give you the exact API request that you need to feed into its harmonized data access, or HDA API client, to retrieve that data in an automated way, or in a program-based way. So this little bit of string here tells me the collection that I'm looking for, my bounding box, and then the time range that I've selected, which in this case is not very long. Well, actually, it is really long, so I don't really want to do that, because that would be a great many granules. But yeah, for now, no. Okay, so just remember the format of that, because I'm not going to choose to download data here. The last thing I'm going to show you is that inside Wekio, there is also a free-to-use Jupyter Hub. So the Jupyter Lab instance that I showed you for the data store previously was on my own computer. This one is not. This is my one. Let's get rid of that one. And let's go to the Jupyter Hub. And I've just clicked on that little Jupyter Hub icon, which, let me just show you that one, this one is right here. This is now running on the Wekio cloud. I'm going to choose my server as Earth Observation Tools. Take a little bit of time to spin up. Usually only a few seconds. It's just preparing my hub for me. Okay, and then similar to what I had running on my system before, I have another Jupyter Lab running, my own one, but this one is on the Wekio cloud infrastructure. So I'm not now going to move any data to my local machine. Everything is going to happen on the Wekio cloud. Now, it can take some practice to kind of find out where your landing point is, but under public, you will find that there are a load of pre-existing tools and packages. Now, if we want to have a little look, if I go back to the Wekio front page, just going to reuse this this browser window. If I scroll down here, on the front page, there's a link that says get started now and points to Jupyter training material on this kind of like fake code implementation. This will take you to a catalog of all the Jupyter notebooks that are currently available on the Wekio system. Now, many of these are similar to the UMetLab GitLab instance I showed you before, but some of them are also much more specific to the Wekio environment. Excuse me, and they show here as well, including one. If I turn off everything, if we scan down here. So these are all existing marine, or some are marine, some are not marine, Jupyter notebooks for working with Sentinel-3 data, including a significant number from Alchi. And then at the bottom here, we've got welcome to the Harmonized Data Access API and welcome to Jupyter Lab. And it's the Harmonized Data Access API one we want. Now, if I click on this, this is going to show me the actual notebook itself and say open in Jupyter. Now, there is a slight problem with that, because if you open it in Jupyter from there, it will open in the public folder. So if I go into Wekio for data, that notebook will exist here, but this is a read-only space. So I can't actually acquire data to this space. So what I've already done before is I've made a fresh copy of Wekio for data in my own in my own private space on my Wekio kind of Jupyter Lab Cloud instance, where I can work and I can actually write to if I want to acquire data. Now, if you want to go and get the code yourself and kind of clone it onto the Wekio system, you'll find all of that code available on github.com/Wekio. And there's Wekio for Oceans, and I'm working in a folder called Wekio for Data. And so the instructions on how to move that code onto the Wekio system are all provided for you under the README for this repository. So to actually get it onto the system, you would just need to run this. So copy that and paste that in the command line here, open a terminal and paste it, and then you will have exactly the code that I have now. So let's look at how the Harmonized Data Access API works. And actually the Harmonized Data Access API is really just a clever translator. What it does is it goes away and it adapts your data requests to the other APIs that underlie it to get data from other places. But those other places are connected to here with massive fat pipes to facilitate data delivery in a more efficient way. So as before, one thing I have to check before I go is that's under here, under select kernel, which I went a bit quick there. You should select mini Wekio lab. And then as before, I'm just going to click shift and enter in all of these gray boxes, and they're going to run as we go. So it's explaining that I'm just importing all the various Python packages that I need. It'll tell me a bit about how I actually go and search for data on the Wekio platform and how I get the ID and the various stuff that I need. But actually, to some extent, we can sort of skip that because we already went and grabbed our exact API request from our browsing through the web UI part. So we can set all of this information about the data that we want, the dataset ID. As before, you need to spend a little bit of time focusing on this to show how you actually authenticate the API to grab the data. Full instructions are given here, so I'm not going to dwell on that too much, but there's multiple ways you can pass the credentials directly or through a configuration file. Because I'm sharing this with you, I'm doing it through a configuration file. Okay, and then the last thing we wanted to do is we take the information from this API request box we opened before, and we can do it in one of two ways. We can either paste that directly into our Python script and give it a variable name, in this case query, or we can bang it straight into a text file and load it in using this little box here, this JSON.load routine. And that has read my pre-existing exact copy of this from this text file. And now if I choose to run this, and tell you what, I'm not going to download it to here for now, but I'm just going to write just so you can see what data we would get. Apologies, there we go. So now it's going to take this query and it's going to throw that at Wekio. Wekio is going to translate that query and pass it on to all the various collections it knows about. And it's going to say, right, here's where the data is. And then if I made a new code sign here, new little code thing, and put back that, actually stop download, it's going to now go away and get the granule, this single granule that I've requested. So you can use the Wekio Jupyter Hub to download data from both the Copernicus Marine Service, as well as the Copernicus Land Service, Atmosphere Service, products available from EUMETSAT, ECMWF, ESA, so Sentinel-1 and Sentinel-2 data is available through here as well. You can gather them all in the same place and access them all through this Wekio Harmonized Data Access API. And you're taking them to, here's my granules, I refreshed seconds ago, a place that's not local. So you can work with some constraints on this remote platform, irrespective of if you're working in a place with bandwidth limitations, or you just want to do some testing without bringing anything back to your local machine. Okay, that was an extremely dense whistle-stop tour of a number of different data repositories, a number of different data providers, how you would select data, where you would go to get data. All of the resources are shared either in this presentation, either as links in the presentation itself, or through these links that are kind of held towards the end on this resources tab. Alternatively, by all means, email me with your questions, or EUMETSAT if it's questions about the broader catalogue. If you're interested in our training calendar, there's a link to that as well. And for those of you that are attending the symposium themselves, yourselves, I will be one of your trainers. So happy to hear any questions you've got about data access or UMETSAT products for ocean color, sea surface temperature, altimetry, as and when you see fit. And that kind of concludes my my fairly dense presentation for now. Happily take all your questions. Thanks.
Thank you very much, Ben. That was, as you say, quite the tour of what is as you said, quite a complex architecture and system, but very, very useful. I think I, as well as many others, will probably go back and look over those video or the slides when we're next thinking about which data sets we need to use. So that was fantastic. We've had a number of questions throughout. So I will start by addressing those, and the rest of the panel should feel free to raise a hand if they want to chip in. If you don't mind, I'll start. There was a couple of questions about kind of things around the talk and about the lecture series. So I'll start with those, and then we'll move on to the lecture material. So there were a couple of questions about getting access to the slides, getting access to recordings of this. So those will all be available. I know I've said this a couple of times. We have the recordings for the first two lectures already edited and uploaded. We're just waiting for final approval from one of the lecture sponsors before we can make them public, but we expect that very shortly. So then this one will also follow and should be available online, we hope, within, say, a week. Then Ben has already provided, maybe you could share that slide now, your first slide, with the QR code. And you could maybe, I don't know if there's a sharing link you could drop in the chat, but that will allow download of the slides themselves, which has, so all of those sections where Ben had the different services with links, you would be able to click those links. So that should be available then as a nice resource for everyone. And I think that's, yeah, that covers all of the stuff around presentations and access to things. So following that, we'll move on to questions about the material covered in the talk. There was a couple of questions came up early on in your talk when you were talking about which data sets you might want to access. One of them was around what would you class as ancillary information at level 1? And do we have, is that something that people have to access, or is it something that is tagged on to the data? Just wondered if you wanted to speak a little on that.
Yeah, quite happily. It depends mostly on a product, and kind of on a product by product basis, but in general, most of the ancillary information, or a lot of the ancillary information you need to work with the product on by itself, is included both at level 1 and level 2. There are some caveats to this. If you are looking to contextualize your analysis with information around the optical and or physical environment around your product, say if you're doing matchup analysis, then it is sometimes necessary for you to get other ancillary data associated with it. So it really is a kind of case-by-case basis, I would say, whether or not you need to get ancillary data or not. Tom, Haley, I think you probably have your own perspectives on this, and maybe you want to add to that fairly broad brush answer from me.
I think it would also, I mean, from my point, it would depend on also the level of data you're accessing. So I know that some of the atmospheric correction schemes might want to ingest ancillary data from models like ERA 5, so atmospheric data. That is included with some of that ancillary information is included, say, at level, like you said, 1 or 2, but by the time you get to level 3, that might not be included. So it depends really what level you're looking at and which sensor you're looking at. But yeah, at level 1, then usually most of the data relevant to processing is included. Flags and all that sort of stuff as well would be included. Yeah. There was also a question during that section about which data is relevant, talking about acceptable uncertainties for combining multiple sensors. So I think this is referring to the level 3 data. We will cover this a little more when it comes to climate data sets. But I don't know if you wanted to talk on that or not. But I think that depends normally on your application, really, whether it's NRT, near real time, if you want something very short, or if you're looking at something for longer climate analysis, so the level 3 or level 4s that you were talking about. There was a question around, a couple of questions around the data repositories, and they're from different providers. So some data may be available from multiple portals, such as chlorophyll from OCCCI, can be retrieved from the CCI portal or CMEMS, or in some cases, there's also a Copernicus version. Is there a difference between them? How do I choose which portal I should get the data from?
Very interesting and slightly complicated question. There are parallel developments that occur using expertise from similar people to produce things that kind of are aligned. In general, I would say that provided you go at least level 3 for a product that comes with a statement that says this is based around a harmonized kind of reprocessing approach, then you probably won't go wrong. I am quite the advocate for the CCI products, but that may be because of the presentations that I've attended and the people I've worked with and the efforts that I know have gone into those over the years. I am, I confess, slightly more skeptical about level 4, where there can be a much larger variety of methodology that's used, either Dinioff, optimal interpolation, other kind of approaches that are used to recreate that data. I would be quite careful with using level 4 data, and I would use, to be honest, probably what is most convenient for you, but I would not particularly base any very hard scientific conclusions on using data that's been statistically gap filled in any way. I'd be a little bit careful with that. I think that's probably all I can really say about this, rather than choosing one product or the other. I think I'd just suggest to be careful a bit more with gap filled products. The same is not true for SST, I should point out, where gap filling is usually done with microwave. This is more of an ocean color specific perspective. Tom, perhaps you want to add to that as well.
I was just going to add, I think, so it would come back to your slide about really thinking about what your data requirements are and what that service is providing. So it might take you half a day of just checking different metadata or different documentation, but if you might find that the CCI data that's available from the CCI portal might be the latest version. They might have a newer version than is on the CMEMS catalog, because there's a time that's associated with handover. But you might find that on the CMEMS catalog, there is a higher resolution regional data set, say 1 kilometer, that has had some local processing done with it that you want to use, because it's got regional algorithms applied on top of, say, a CCI remote sensing reflectance. So I would say when you find those different access points, sometimes it is effectively the same data, so through different portals, but just check the metadata or the documentation and see which one is most suitable for your application. And if it's not clear, contact the data providers, because usually they will respond. There is a question that talks about it uses the term freshness of data, but I think it means the time lag. So the example given was that, on a repository, say oceancolor.org, that you said, the latest product might be from the 7th of April. And obviously that's got, say, a 2-week lag time at the minute, whereas in some repositories you can find data from yesterday or even today. I wondered if you wanted to talk a little on that difference you'll find with different data sets and when it's important.
Yeah, I'll quite happily talk to this point. To give an example, for Sentinel-3 Algae data, we have data available at 2 levels of timeliness. We have near real-time data, which is the data that comes out the quickest, but also has the I wouldn't say compromise, but has to make choices with regards to how it gathers ancillary data and how it actually does its retrievals based on, say, for example, forecast modeling for wind fields. Now, this data is available very, very fast, but the caveats associated with that approach have to be taken into account. If you're willing to wait a little bit longer, you get to the delayed time data, then the wind fields are related to actual observation, and some of the other ancillary data that's included is more readily available, so we can give a higher quality estimate for the actual retrievals in the delayed time. The other part to that is, over time, we have changes in processing structure, we have changes in calibration, and so we probably want to revisit the entire record over time, to update the processing to the most recent understanding of how we can actually work with this data. At this point, we would have a reprocessing campaign, which happens on average maybe once every 2 years or something like this, where we actually revisit the entire record, update the processing to something consistent. If you can afford to wait for the latest reprocessing of a data set, then that will give you the highest quality data that you need. But the question really is the result of how fast you need the data and what you can actually wait for in terms of your application of need. In practice, I would say that the wait from NRT to DT, so near real time to delayed time, is not so large, but the wait from delayed time to reprocessing can be substantial. And I would always say, be very aware of trying to take a reprocessed time series and stick a near real time product on the end of it, and to try and treat them equivalently, because they are not.
Very, very clear. I don't know if the panel wants to add any more, but that's yeah, very, very well covered. There was a number of questions around the tools that you demonstrated. I think most of it, or some of them, were answered in a self-evident manner. People were asking about whether or not you could access the same region for 10 years of data using the packages. I mean, I think you demonstrated quite well that that's possible, but you maybe want to check how much data is going to be downloaded before you click go.
Yeah, so some things to be aware of there. As you saw from one of my little quick examples, I nearly clicked yes on downloading 332,000 granules, which would have been everything for Algae ever over the globe. So you do have to take some care. There is an inherent difference and slight that you should be aware of when performing this exact thing with regards to level 2 versus level 3 data. Level 3 data being consistently gridded, you can spatially subset, and you will have the same size net CDF grid for every timestamp. That is not true at level 2. You will get a load of granules that overlap to some extent, or perhaps don't overlap, but are just within your bounding box of interest. And then you will have to perform some sort of analysis yourself to pull all of that together. That is sometimes necessary, but processes like level 3 binning, for example, are precisely for this this kind of approach. They are not trivial, but sometimes you are forced to go this route. Yeah, you can download as much data as you want. If you ask for a significant amount of data, expect the providers to somewhat throttle you, because everybody really operates on a fair use policy, and the whole community uses these services. But it's possible. Everything is available on demand should you want it.
There was a number of questions around different products that might be available. I mean, I think I would recommend, we don't necessarily have to answer all of this here, but the search functions for most of these services are quite robust. So we had requests about rainfall, or suspended particulate matter, or phytoplankton groups. I mean, you demonstrated a number of those. I know there's definitely TSM or SPM products available from some of these repositories. Rainfall is one I'm not so familiar with. I think there was something in the NASA Earth catalog around, was it iMerg or something like that, where there's a merged precipitation product. But I would just recommend go and search. I don't know if you can add much to that, but there's a lot of products.
The only thing I could say is, for rainfall, if you're comfortable with reanalysis data, then you can always look at the ERA products from ECMWF. They have their own APIs for access. Word of warning, licensing will stop you from getting near real-time data from that, so you will be limited a little bit to, I think you can't get the last 15 days before now, but if you're looking historically, that should be available.
There was a question around if you know where to find a database of WebGIS links to data sets such as EUMETSAT NASA. I think you actually provided that on one of your slides. I'm going to class that.
Maybe I'm it. Maybe one of my slides was it. If I'd have found one, I would have pointed you towards it. So I'm afraid not. I wish there was.
There was also a question from the well, there was two questions. One around the CMEMS demonstration and asking about downloading large data sets to open using CDAS, but it also links with a question we had asking about looping over or having lots of small areas you want to download, and would you recommend putting all of those into a file and looping over with the API, or is there a slightly more
this is something I've done quite a lot, and CMEMS has a cutoff data limit of around about 1.2 gigabytes. If you request something larger than that via the API, it will tell you it can't. So my approach has always been to cut by time and to loop over time. But if you're dealing with a non-contiguous area, then I would just throw each one of the areas. If you have to go by time and area, then do it like this. But if your area is continuous, don't try and cut your area. It's much easier to aggregate by time later than it is to stick all the boxes back together spatially. So that would be my advice.
We've had a question about maintaining reproducibility of downstream developments, particularly with AI, when the EO processing methods or data versions change. I guess this would come down to having versioning on your data sets and tags and DOIs and all this sort of thing.
So versioning of the data sets, from at least speaking from a EUMETSAT perspective, is all encoded in the XML manifest files for SAFE. They've actually just been updated as well to include more information on the processing baseline that's included within those. Also, whilst we engage regularly in up-to-date reprocessing campaigns, that doesn't mean the old reprocessings go away. They just tend to be backed up. I believe there are ongoing discussions about how we actually provide referencing for those in perpetuity. This might be something that Hayley wants to speak to. I think you have more of a handle on this process.
You mean about things like trusted provenance and that sort of thing? Yeah, so this is an ongoing issue of trying to figure out how do you embed the information that's inherent in the processes in the actual data itself. So when the products leave us and they end up in CCI or in CMEMS or in somebody's analysis in a paper, how do we know what version of what they used? And this is very difficult at the moment to do, but there is ongoing work around this idea of trusted provenance in order to see if we can make that more clear. At the moment, the best way is to ask the people at the various steps of the chain. If you're not far from the providers, it's normally not too difficult for us to find and provide that information. That's part of the job that I do. For example, if you contact EUMETSAT, it'd be me who'd help you with that kind of thing. But otherwise, yeah, I would say in general, you're going to want to try and make your workflows responsive so that when a new reprocessing comes in, you can automate redoing your analysis effectively quite efficiently. I know it's difficult. This is an issue for anybody who uses products from an upstream provider. And so this is why we try to find that balance with not reprocessing too often so that people don't have to do too much work downstream, but also responding well to improvements or needs to make sure the data is as accurate and appropriate as possible. So it's a fine balance, but yeah, be happy to talk more about that in person in the symposium as well. It's a good topic.
And I guess linked to that, there was a question around the use of EO data and commercial use of data and licenses. Now, you did mention that many of the data sets you covered are public and open access, and you can do what you want with them. And sometimes you run into some licensing issues. I guess that's also one that is a case of just check before you do anything.
Yeah, if it provided its Copernicus data, and then it's completely free and open for whatever purpose you want. Scientific, commercial, use as you see fit. I can't speak to all the data that's made available here, especially for some of the higher resolution stuff. They're probably not true. In fact, certainly not true for the solely commercial stuff.
I don't know if you mentioned the future and a world in which moving the data gets harder and harder because it gets bigger and bigger. And we did have a question about hyperspectral missions, and as we move into having more hyperspectral missions, and how that data might be available. I guess that's more a case of you go to the data than the data comes to you.
Yeah, I mean, fully like heart on sleeve, this is a fairly circumspect conclusion from me, but I don't see any other way that we're going to be able to work with this data across the community, and working via duplication is going to be extremely difficult. Hyperspectral is obviously one avenue in which the data is going to become enormous and very, very hard to deal with, very hard to move. And the last thing we want to do with hyperspectral data is reduce its complexity for the sake of convenience. So, yeah, I think upcoming missions like Nmap, missions like PACE, missions that are completely going to start to deliver us data in massive density. We have to find new ways, new platforms, new approaches to having APIs that facilitate processing. I think basically you wrap up your process in a little box and send it off to the data rather than vice versa. And in order to be able to do the analysis that you do at one of 3 master records globally or something like that, I don't think there's any way around this. I think this is the way it's going to have to go.
Great. I mean, I think so. I've seen a couple of people have had to apologise that they've got other meetings to go to. I think 1 or 2 more questions, and then I think we'll wrap it up. So there was a question around. 1 second. You mentioned using Dask, which is a distributed analysis system. I just wonder, and we've seen there's other packages being developed on top of things like pandas and other, geopandas and things. How well do those interact with things like the remote Wekio system? I mean, can you use all of that, or is it at the minute limited?
Okay, so Dask in particular operates, or most of these parallelization programs operate under an understanding that you have resource to expand into. So Wekio offers a number of different cloud services, one of which is the free Jupyter Hub. But in order to deploy Dask appropriately, you need like a bank of VMs in order to be able to exploit. You can talk to Wekio about spinning this up, but now we start to move into, an actual cloud service that needs to be paid for in terms of infrastructure. So ask the question, but I would not expect anybody at all globally to offer you free cloud compute for highly parallelizable tasks. Just to give you an example, I span up a small Dask workflow on $200 of free Kubernetes that I got given by Google just by signing up, and I used it in 3 days. So, it's when you start to move into extreme parallelization, then there does have to be an infrastructure cost associated with this.
Yeah, so at the minute, the Wekio is very good for testing and trialing, and
yeah.
If you wanted to bulk process, then that's
the infrastructure is there, but the infrastructure is not free for people to just play with as they wish, because it's very easy then to ask for all the resources.
Okay. And there was let's have a quick look at last question. While we're on the topic of Wekio, someone was asking about the difference between, say, Wekio and Google Earth Engine. They are currently using GEE, and was wondering if maybe they should also use Wekio. I mean, I think upskilling, as it were, learning to use more of these tools is always a good thing. But I don't know if you wanted to talk about any of the major differences you might know of between GEE and say Wekio.
Infrastructure-wise, they're quite different, but I think one of the first things you're going to run into if you try and work with GEE is there is very little marine data on there. So none of the catalogs host any marine data, and the simple reason for that is people don't live in the ocean. The land data is considerably more valuable to someone like GEE than the marine data is. They prioritize those collections, and they're much more likely to grab everything from Sentinel-2, Maxar, Planet before they go near Algae. So I think if you're hoping for GEE or AWS ingestion of ocean color products, you're going to be waiting a long time. Wekio, it's available there now.
Thank you very much. I mean, there was a number of other questions floating around about where to get data for different products, or what might be suitable. I would say, again, go back, look over Ben's slides at his level and what realm you're interested in, and you'll probably find somewhere in that wonderful matrix a best first guess. Beyond that, contact the data providers. Yeah, I think with that, thank you very much, Ben. And I think we'll draw the talk to a close there. Thank you all for attending. It's been fascinating.
Thank you, everyone. My pleasure. Cheers.
Thank you very much, Ben and Haley.